that the momentum initially, right, the left side of our equation equals the momentum after in the system, right? And in this case, the system is the two cars. All right, so what we know is that both cars have momentum. All right, so what we need to do is figure out how much momentum was there beforehand, and then how much is there afterward. It's going to be the same. So the first one, let's see here, car C is going north. And it's going north at 27 meters per second. And its mass is 1325 kilograms. So that means it has momentum north. Car D is going this way, and its mass is 2,165 kilograms, and it's going east at 11 meters per second. So it has momentum going that way. This is happening before they collide. So let's put this little line here. That'll separate out before the collision and after the collision. Right. So there is momentum here. Now how much is there? Right? When it was in one dimension, it was just a simple matter of this momentum plus this momentum, right? It's in one dimension, you add them together. But now it's not in one dimension, right? It's in two dimensions, and momentum's a vector. So when you have vectors that need to be added in two dimensions, you have to do your triangles, right? You have to do your vector addition. So what we're going to do is tip-to-tail method, because that's how you add vectors. So this car, C, has a momentum going north equal to the momentum of car C, and V is 1325 times 27. So car C has a momentum of 35,800 north. Car D has a momentum this way. Again, mass times velocity, and that is 23,800 east. So now we need to add those two momentums and figure out what the resultant is. So the resultant is, you do the Pythagorean theorem, and you get 43,000 kilogram meters per second momentum. All right, and the direction of that momentum is, you could find this angle here, use your inverse tangent, we'll call this angle theta. So theta is inverse tangent 23,800 over 35,800. And so that's going to be 33 degrees east of north. That's 33 degrees. So that is the momentum initially, right? 43,000 kilogram meters per second, 33 degrees east of north. That has to be the momentum afterwards, because the momentum is going to be conserved in this case. So let's say the collision happens right here. The momentum needs to keep going that way with that magnitude. So what we know is that our final momentum is also 43,000 kilogram meters per second, and that's your 33 degrees east of north. But now the question is, how fast are they going? Well, they become one mass after the collision. So the final momentum actually equals the mass of C plus the mass of D, because they're stuck together, times their shared velocity. So that's going to be 43,000 equals 1325 plus 2165 times V. That'll be the final velocity. So VF is 12.2 meters per second. And remember that the direction of the momentum is the same as the direction of the velocity. So if the momentum was 33 east of north, then so is the velocity, 33 east of north. And that's how you get it. So we're still using this equation. It's just that to add them here, since they're not in one dimension, you have to do vector addition. So this implies vector addition in this case, because they're at right angles to each other. you couldn't use velocities because velocity is not a conserved quantity. So if you try to make your triangle as 27 and 11, using the velocities of the cars, you would get 29 as your velocity, which is not correct. Okay, because velocity is not conserved, momentum is. We used this when we were getting relative velocities, but that's not what this problem was looking at. So you don't do that.